Nicolas Gigena. Nico is a reference in quantum info, quantum correlations, and so many other things. He's from Argentina and studied physics in, I think, is the most important center here, which is in Bariloche, is Balseiro, is from nuclear people. And can you share? Are you sure if you can share?
Yes, I think I have to share my entire screen so that I can just go to presentation mode here.
Ah, okay, cool.
Like this.
Well, I keep on. Then Nico did a PhD in quantum computing and quantum information, and I guess strongly correlated systems as well. More or less.
More or less, yeah.
And then a postdoc in Warsaw, is that correct?
In Warsaw, yes. On non-locality and that kind of stuff.
And now he's a staff in the research center here in Argentina, in CONICET. And I'm fearing that I don't know if you can actually share or not. Because some people have trouble with this.
You should be looking at my presentation now. Are you not?
Me, I'm not.
No, me neither.
I hate this. Oh, no, I think this is the problem. Now you should.
Yes.
Yes.
Okay, fantastic. So let me, the thing is, since I'm sharing the entire screen in order to go to this presentation mode, I don't see you. So I will ask if there's something you want to ask or you want to interrupt me, just go ahead. Don't raise your hand because I won't be able to see you. So yeah, that's it. So if you want, I can just start.
Yes, Nico, please. And thank you really very much for preparing this talk for us today.
Okay, thank you. Okay, so as you can see in the title, it's a not so gentle introduction to quantum correlations, mostly because while I was kind of doing this stuff, some things happened and I underestimated the time it would take to me to go through all the things I wanted to say. So, well, I had to cut a couple of things, but I hope most of it will be easy to follow. And if not, you can interrupt me at any time, and that's just fine. So this is about quantum correlations. I will try to do a quick summary of first non-locality and how it allows for certification of quantum devices. And then I will just jump to some main results on entanglement theory. And let's hope it's enough. So let me begin with non-locality inequalities. So we will be thinking most of the time on a device-independent scenario. So what we're considering here is that we have here Alice involved, and they have these boxes. They don't know what they have inside, and in order to know something about them, they can realize some measurements that I marked here as X and Y, and these measurements will have some outcomes, A and B, with some probabilities. And we're interested in correlations, so we're interested in the joint probabilities of outcomes A and B resulting if we measure X and Y. And of course, we will say that there is correlation if these joint probabilities do not factorize like this, right? So let's characterize this a bit better. So suppose in a given experimental run, Alice and Bob decide to perform 1 out of m possible measurements that will be labeled with X and Y. And for each of these measurements, we will have outcomes A and B respectively. And let's say we have V of this for each measurement. Then we have m squared times d squared possible joint probabilities like this. And in order to make sense of this, let's couple all of them in a vector in a real space of dimension m squared d squared. Of course, not all vectors in this space will be behaviors in the sense that they have components that are probabilities coming out of this experiment. Of course, because these components are probabilities and they have to comply with the usual constraints we have for probability distributions. But moreover, we will have some extra physical constraints on these behaviors. So the first one is no signaling constraint and is given by these linear relations here. And it doesn't really matter what these equations say. I mean, in terms of words, what this condition mean is that what happens to Alice's marginal is independent of what Bob decided to measure on his side and vice versa. So this is some way, well, this is why it's called no signaling. And this is in some way something complying with special relativity. The other physical constraint we can impose here is the locality condition, which I've written here. And again, this may seem a bit odd, but all it says is that correlations we are assuming that arise from some kind of shared randomness and local preparations. So if we think of these two constraints, these are all linear, and because they are linear, they define a polytope in this real space of dimension m squared times d squared. Well, this polytope, the interior of this polytope contains all the behaviors complying with the no signaling condition, and some of the vertices of this polytope are also local in the sense that, well, they are local deterministic behaviors. Now, the convex hull of this subset of vertices is known as the set of local behaviors, and this set of local behaviors is the set of all the behaviors complying with the locality condition, right? And this is again, since it is the convex hull of a set of vertices, it is again a polytope, right?
Nico, I will interrupt you,
yeah.
okay?
Yeah, sure.
So, just to clarify a bit, because maybe I feel I will confuse a bit, and if I get confused, then it's super likely that more people get confused.
Sure.
So the first thing is that when I first heard about a polytope, I got a bit confused. And can you clarify a bit what a polytope is? And the second one is what can you define again these behaviors? Is like what the probabilities are, or?
Oh yeah, sure. So first of all, let me go back.
Sure.
Back here.
Thank you. I'm sorry for
no. That's perfectly fine. I was expecting this. So cool. As I said, since we are interested in these joint probabilities here, and we have n possible measurement settings, and for each measurement setting we have the possible outcomes, then we have m squared and d squared of these possible probabilities in a given experimental run, right? So what I'm proposing here, I mean, we don't have to, but what I'm proposing, because I think it is useful, and I mean, not me, most of people does, is that we can join all of them in a given tuple and think of it as a vector in a real space of dimension m squared d squared, right? So we just form a tuple with all these joint probabilities and think of this as a vector. And this vector is what I am going to be calling here a behavior, because in some sense, it kind of says how the system, this joint system of boxes behaves when we perform measurements, right? So from now on, we will be thinking on vectors on this real space, thinking that the components of these vectors, these behaviors, are the joint probabilities we can observe when measuring on these boxes, right? And then I said that we have these two set of conditions, no signaling conditions and locality conditions, and these are linear conditions, right? You can see the equations here. Now, because these conditions are linear, we can think of this set of behaviors complying with these conditions as that resulting from the intersection of a finite set of hyperplanes, right? In this highly dimensional real vector space, right? So if we think of this of the intersection of all these hyperplanes, what we have is something that in higher dimension is kind of pretty analogous to a polyhedron, right? So in the same sense that a square can be thought of as the intersection of six, as a cube can be thought of as the intersection of six planes in dimension 2, well, we can think in a higher dimension that something which is analogous is something that you can think of the intersection of a finite set of hyperplanes, right? And that's basically a polytope. It's a higher dimensional analog to a polyhedron in dimension 3, right? So I'm guessing this is clear enough.
Yes, it's super clear. And just to put a bit more of context, what you're studying, if I may, sorry for the atrevimiento. What you're studying here is which are the outcome probabilities when you perform measurements and you have correlations between two players, right? Or two parties.
Exactly.
And all this complexity arises, you're imposing some physical constraints, these linearity conditions, locality, etc. Give rise to this super complex polytope. But this is only for the two players, and is this correct?
Oh yes. This is bipartite. I'll just restrain myself to bipartite systems here, just in order to make it easy. But of course, you can generalize this to scenarios with more parties and whatever, right? But for now, I'm considering only two parties, right?
Okay, cool.
Okay, so once we have done all of this and we have this little polytope here, the first thing we can check in the general case is that both these sets, the no signaling set and the local set, have the same dimension, which is in the general case given by this equation here. It's not really important, but the point is that since we have imposed some linear constraints, the dimensionality of our actual set goes down with these constraints, right? So now the point is, I mean, everything is just fine, but we have imposed a couple of physical constraints that have to do, first of all, with, well, I mean, preserving no signaling condition to be okay with special relativity. And I've also introduced this locality condition, which is more or less a nice ways to think of how things can be correlated, right? So if you think of the most general protocol to correlate something classically, and this is the kind of correlation that you will attend. So, but there is another physical constraint that we can impose, and it's about probabilities coming out from quantum states and measurements, right? So if we think of this, I mean, we know quantum mechanics is a probabilistic theory, and if we have a bipartite system in some state, in some Hilbert space, and we want to perform a joint measurement like the ones I have been describing so far, then we know, because of Born rule, that the probability of outcomes A and B given X and Y are given by this expression here, right? So this is a physical constraint that basically says, well, I mean, our probabilities are coming this way because inside these boxes, we might have quantum systems, right? And of course, well, this rho here is some operator from over this Hilbert space, and also these operators EAXA and EYB are operators on the same Hilbert space, representing the possible outcomes of measurement settings X and Y, right? And of course, what I'm thinking here is that the joint Hilbert space in which rho lives is the tensor product of the state of system A and system B, which are the systems being shared by Alex. Now, you can prove that the set of behaviors satisfying this quantum constraint, which I call here Q, is a convex set, but it's not a polytope. And the other thing that you can prove in the general case is that this inclusion relation here holds. That means that somehow Q is kind of sandwiched in between the local set and the node signaling set. And of course, since these two have the same dimension, the three sets have the same dimension, right? Now, I said this set is not a polytope, and actually the boundary of this set is quite complex and is very hard to describe in general, right? And most of the difficulty here comes from this thing that I added here, which is we are not imposing any constraint on local dimensions when we say that a behavior might admit a quantum realization, right? So this makes things very, very complicated. Okay, so why I'm interested in the boundary of this set? Well, first of all, because it is just interesting and that's it. But on the other hand, it is interesting, I think, or I understand these are the two most interesting reasons. First of all, there is this quantum reconstruction program. This is a subfield in quantum information in which people tries to kind of reconstruct quantum theory out of first principles in information theory, right? So one example of this is, I don't know if you know it, but information causality is one example of this, right? In which an informational principle on communication imposes a constraint on the amount of correlations that you can have between quantum systems. And well, there is some work on this. And from this point of view, knowing what the set of correlations of quantum correlations is, somehow is something that you can use to kind of check if possible proposals for quantum reconstruction make sense or not, just by checking if the predictions of these reconstructions of quantum theory are consistent with what we know of the set of quantum correlations. The other reason is much more practical, and is that the boundary of the set of quantum correlations is very closely related to the task of certification of quantum states and measurements. And I'm gonna go back to this later on. But basically what happens is that you can use behaviors on the boundary of this quantum set to certificate that some probability measurements are coming from just one possible state and set of measurements up to local isometries. As I said, I'm gonna come back to this, so we can skip it from now. Okay, so the point is there are good reasons for studying this set, and the question now is, well, how, right? So one tool, the one that I have most used so far in order to study this, is Bell functionals. So we can, in general, for all three correlation sets, we can probe the boundary of a given set, any of three, by thinking on the maximum of a functional in the real space in which behaviors live over the behaviors in a given set, right? So this is what is written here. And the set of points that maximize a given functional define what it's normally called in polytope theory a phase, right? So in order to be clearer here, let's use the simplest case, which is the case of the local set, right? Let's assume we have some functional on this real space, and we want to maximize it, because the local set is a polytope, then the maximal of any functional here is attained at some of its vertices, right? So this means that we can have phases defined like this of dimensions in between 0, which is just one vertex is maximizing the functional, up to, it says here, t minus 1, and t is the dimension of the local set. So one dimension less of the dimension of the local set is the maximal dimension that we can have for a facet. For a phase. And these t minus 1 dimensional phases are called normally facets. So let me see if I can be more clear here. So as I said, we can think of this polytope either as the convex hull of some set of finite amount of vertices, or as the intersection of some finite number of hyperplanes, right? And this is what defines this polytope, which is kind of very similar to a polyhedron. Now, these phases somehow, how to put it? These phases are associated or are supported by these hyperplanes I was talking about. And because of hyperplane separation theorem, these hyperplanes, which are associated to these functionals, we can associate to them an inequality like this that will basically tell us if we are on the interior of the local set of the polytope or if we are out. So if we maximize the, if we look at the value of a single behavior here, P, on the functional, and this value is lower than the maximal value for the local polytope, then we have a local behavior. Otherwise, we have something which is not local, right? And you can see that because of this, these hyperplanes and the inequalities associated to them can be used in order to identify which behaviors admitting a quantum realization are local or not, right? And we will be mostly interested in those behaviors which are not local, but nonetheless admit some quantum realization, right? So,
but in general,
just
do you know beta?
Sorry.
The bound, the upper
yeah,
bound is known.
Oh yeah, you can always calculate it because, as I said, the vertices of this local set are given by local deterministic behaviors, and for any scenario, you can just name them. You can enumerate the vertices, and you can just compute the maximal of a given functional over all the vertices and just keep the largest one. So this is very easy to compute, although it becomes like really inefficient when you go up in space dimension. So for larger scenarios, I mean, you can always do it, but for larger scenarios, this becomes like pretty efficient. But in principle, you can always do it. So this is something that you can always compute, and is again kind of easy but inefficient for larger scenarios. So this is something that you can always compute. You know the value of these things, so you can use this to decide whether a given quantum behavior is inside the set of local behaviors, or is it outside and is therefore non-local, right? Okay, so more or less, furthermore, we can use these inequalities to decide just the membership. I mean, not just looking at the violation of just one inequality, but we can look at all of them and solve the membership problem, which is something we can implement with a simple linear program, which again, at higher dimensions will be inefficient, but for the smallest scenarios, you can do it pretty easy. Okay, so this is kind of a warm up to justify why it is okay to look at Bell functionals in order to study the boundary of a correlation set. And we have seen that for the local set, this is pretty easy, and we can attack it numerically with a linear program. Now, if we go to the quantum set and think about doing the same, well, it becomes significantly harder because, as I said before, the quantum set is not a polytope, right? So if you want to describe phases of the boundary of this set, we have to basically compute these maxima for a given functional, right? And since we have to optimize this over all quantum behaviors, this is, like, in general, a very, very hard problem to solve. And in the general case, of course, there's no analytical solution for this. And in most of the scenarios, there are no analytical results. In fact, there is only one case in which we have full analytics for this, which is in the simplest scenario, which is this one I'm going to describe here. So the simplest scenario here is the following. Again, we have Alice and Bob. This is bipartite. And we have that each of them will perform only one of two measurements, which I label here with X and Y, that take values 0 and 1. And we will say that, again, this is the simplest case. Each of these measurements can have outcomes A and B, which can take values only 1 and -1. Now, in this scenario, and with this setting here, it is easier to go from probabilities to marginals and correlators. I guess you are used to these expressions here, but this is just a linear transformation from probabilities to these other guys, marginals here and correlators here. And the reason is that it is just easier to work with this. That's it. So in this setting, we have that the dimension of the three sets is 8, and we can give a given behavior in terms of a notation like this. This is just a parameterization again. And we have basically 4 marginal components to a behavior and 4 correlator components for the same behavior. So this is 8-dimensional. Now, it's not
Nico,
hard to see.
Sorry. I have one question from the previous slides. You go. You say so. Is it obvious? It's obvious, no? That describing the probabilities is equivalent. The full probabilities to this one and two body one body correlator, to the marginal and the 2 body correlators, just because it's 2 parties, no?
Yeah, I mean, this is a result of imposing all the constraints that I've been talking about before, and just using a reasonable parameterization. You can reparameterize this in other ways. I mean, there's nothing forbidding it. It is usual to go this way because, as far as I understand, this is the simplest way to write the behavior. But of course, you could also just stick to probabilities and write everything in terms of probabilities, and that would be just fine. This is just a parameterization, right?
Because in principle, you're jumping from an m² times d², if I recall correctly, vector to an 8-dimensional vector.
Okay, that's a good point. So as I said, you have 2 measurements per party, and each of these measurements has outcomes, 2 possible outcomes, 1 and -1, right? So in principle, you have 16 of these joint probabilities. Okay. Now in this, and of course, you will think of this tuple, 16-dimensional tuple, as a vector in the 16-dimensional real space, right? But of course, this is before imposing the constraints on the probabilities, right? So we have to impose, of course, the normalization constraint and positivity constraint, but also the no signaling constraint. And if you impose all these constraints, dimension goes down from 16 to 8, right? And then in this 8-dimensional space, you look for a reasonable parameterization, and it is the consensus that this is the best way to look at it. As I said before, you can stick to probabilities, and that would be just fine, or you can look for other parameterizations, and that would be the same, right? So this is just a way of parameterizing the thing that makes things easier to look at. So thanks for this, because I jumped too quick to the 8-dimensional thing. So we start in dimension 16, impose constraints, and end up with an 8-dimensional set.
I'm
And
sorry,
behaviors,
I will insist with another stupid question.
yeah, sure.
In principle, you could look to other momenta, no, of the distribution. You could look to a to the square times b, for instance.
Oh yeah, actually, I'm gonna go there in a while. But yeah, for sure,
okay.
you can look at many moments of the distribution. But again, recall that we are interested in correlations, and correlations are basically coming out of joint probabilities of measurement results. So in principle, in order to talk about correlations, it is just enough to look at these behaviors here, right? Okay, so we live in this 8-dimensional set here, and behaviors have kind of this shape. And now it's not obvious, but you can prove that in this simplest scenario, in which you have, again, 2 dichotomic measurements per party, there's only one non-trivial facet of the local set, which is given by this inequality, which I think all of you know for some reason, which is CHSH inequality, and it has a local bound of 2 square root of 2. So what this means is that this linear combination of correlators is lower than 2 square root of 2 for all behaviors inside the local set, the set of behaviors satisfying the locality condition. So as you can see here in the picture to the right, in gray, we have, I mean, this picture is just a slice of the 8-dimensional, it's a 2-dimensional slice of the 8-dimensional set. And it is defined by 2 vertices, 2 non-local vertices of the no signaling set, which are the vertices of this gray square out here, right? Now, the local set is this square here, and sorry, this is the quantum. 2 square root of 2 is the quantum value. So if you look at maximizing this functional here on the local set, the maximal value, which again is attained at some vertex of the polytope, is 2. Is this 2 here, right? So in this 2-dimensional slice of the 8-dimensional set, you have this square representing the boundary of the local set in this slice. Now, contained by it is what should be the boundary of the quantum set in this slice, which is this purple circle here. And the radius of this purple circle is 2 square root of 2, and this is the maximal value that you can attain for this Bell functional here with quantum realizations. That is, with probabilities coming out of quantum experiments, right? And of course, this circle is contained by the gray square out here, which contains all the no signaling behaviors, right? So what we see here, pretty easy, is that some behaviors in the set are local, and all of them admit some quantum realization, and this is why the square is contained in the circle. But some quantum behaviors are not satisfying the locality conditions, so they are non-local quantum behaviors, and they live outside the square but inside the circle. And of course, out of this, there are behaviors that cannot be realized with quantum measurements, and as far as we know, they cannot be realized physically in any way. Okay, so what I wanted to say here is that this is the simplest case, and in this case, and looking at just some subspace of the 8-dimensional space, a 4-dimensional subspace of the 8-dimensional space, which is the 4-dimensional subspace that results of making all marginals in our behavior equal to 0, which corresponds to maximally mixed marginal distributions. In this 4-dimensional subset, we have an analytical description for the boundary, which is given by this relation here, which is normally called TLM condition for Stilson, Landau, and Pasanes. So any point on the boundary of this quantum set in its restriction to this four-dimensional subset is saturating this inequality here. And this is the only example we have of an analytical description of the boundary of the quantum set, right? So, I mean, this is just to stress how hard it is to describe this thing. Of course, if we go from this four-dimensional subspace and consider the entire eight-dimensional set, we don't have an analytical description. And actually, even in this most simple case, we see that the boundary is pretty weird. So this is an example of it. So in these squares here, I'm encoding the components of a wave functional. So if we consider, in this case, the functional with these components here in the square below, then we can check that this functional is maximized both by the point maximizing CHSH and also by a classical vertex, a local vertex of the local set, right? Now, what this means, because
Sorry, I think that we missed Nico. We missed the sound.
We cannot hear you. No.
No, now you
I cannot hear you. Now, yes.
Now, yes. Yeah, somehow it changed itself to the other microphone, which is okay. But now you can hear me.
Yes.
Okay, fantastic. So I can go back. So what I was saying is that, so I stopped here and I said this is the only case in which we have some analytics for the boundary of this set of contour relations. But as soon as we go out of this four-dimensional space, we have real things. Of course, we don't have any more an analytical description. And we can actually see that the boundary here is quite complex. And I was just saying that we have here an example.
Sorry, Nico,
yeah.
just to make sure you are not sharing now.
Oh. Am I? Because yeah. My fault. Because I didn't. Yes. Now I'm sharing, right?
Yes.
Okay.
Yes.
Okay, fantastic. So what I was saying is that here we have an example of how weird the boundary of the set can get. Again, this is the simplest scenario, but we're considering the eight-dimensional thing. And here we have an example of a Bell functional that is maximized both by the same point that maximizes the famous CHSH functional, but also is maximized by a vertex of the local set. Now, because the set is convex, this means that the segment joining these 2 points is part of the boundary. And this means that the boundary has this at least one-dimensional flat face. So this kind of gives an intuition of why it is so difficult to describe this. And I think the main difficulty here is the observation that, I mean, this is a proof that not all boundary points are extremal. So while it is true that the set is convex, and you can always think of a convex set as just the convex hull of its extremal points, the fact that not all boundary points are extremal makes the description of this boundary like pretty hard, right? And I think this is the main difficulty in finding expressions that characterize this boundary in the general case. Okay, so we just renounce to analytical descriptions for it. So we can try to, well, find numerical things, numerical values or numerical approaches for describing it. So as I said, we are looking at Bell functionals as the tool, as the favorite tool for looking at the boundary of the set. And points on the boundary are the points that maximize the value of different functionals in the correlation space. So at the end of the day, we have to deal with an optimization problem, which is the one which is here, right? This is the maximal value of a Bell functional over the quantum set. So what we have to solve is this optimization problem here. And as I said before, since there are no restrictions on the Hilbert space dimensions in which we can consider this, the search space for this is like huge. And this makes the problem like pretty hard to solve. And because this is hard to solve, we have to look for numerical methods to approach it. And I will stick for this talk to this one, which is a moment relaxation, which was introduced in 2007 by Navasquez, Pironio, and Dassin, right? And I mean, in a few words, what this is a way to approach the boundary of the set from the outside with some hierarchy of semi-definite problems, which I'm going to explain now.
Nico, before jumping to there, I have a question. These coefficients that for the CHSH case were -1, here in the general.
Yeah.
Well, -1 to the a times b, no?
Yeah, exactly.
In the general case, beta abxy is given by what?
It's just some real number that, again, I mean, this, you can think of these coefficients here as the component of a vector defining a functional on a linear functional on this probability space, right? Mm-hmm. So you can think of this as the components of a tuple in this real space that is basically pointing to some direction, right? And you're just computing the inner product of this linear functional with your behavior. And well, this scalar value here is just the value of this inner product. And you want to maximize this over all.
But I guess,
yeah.
Okay, when you're taking maximum overall on the POVMs, then I guess that the specific value can be absorbed in this optimization of beta, I say, like the coefficients.
Sorry, I didn't understand. How?
Because beta can be -1, 1, or any real number, right?
Mm-hmm.
But in principle, it's kind of fixed.
Oh, I guess I understand where you're going from. Yes, of course. As I said before, kind of the thing you care about is a direction. You can think of these functionals as just pointing to somewhere in this real space. And of course, the coefficients of this, I mean, given a direction, you have infinite points in real space that basically point in this direction, but they have different norms. And of course, this means that you can think of many equivalent Bell functionals that they differ in the Euclidean norm in this space. And of course, the values of this will be shifted or rescaled by this. But if you want to maximize over a set, then all of this, I mean, is irrelevant because you're maximizing over the behaviors on the set. So the actual coefficients of this doesn't really matter. What actually matters is the direction in which the functional is pointing in order to maximize. But you are right that you can, I mean, given a direction, you can define many functionals that will be equivalent in this sense, and they will give you different values. I mean, is this clear or?
Sí, yes. For me,
right,
yes.
Right. Okay, fantastic. So as I said, This is a very complex problem, and what I'm going to be describing here is a numerical method to approach this, which basically consists of a hierarchy of outer approximations to the set of quantum correlations. So I will just try to describe the intuition behind the method and not go into the deeper things of it, because I mean it's endless. But the point of the approach is the following. Suppose you have some quantum realization, which I'm giving here in these curly parentheses, and these give rise to some behavior which has components P, alpha, beta here, which again, because of Bond rule, you can write like this, right? Now, if we define this set S1, in which we compile the identity operator, operators on Alice's side and operators on Bob's side, and we define a matrix gamma in which the entries of this matrix are basically given by this inner product here. What we have is, by construction, that some of the entries of this matrix will correspond to the probabilities defining our behavior. And there will be some other extra probabilities. But again, by construction, this matrix is positive semi-definite, and also its entries have are constrained, have imposed some linear constraints that has to do with the fact that these operators here in the set S describe quantum measurements. I won't go into the detail of these constraints. The only thing that matters is that this matrix has to be positive semi-definite by construction. And also there is some constraints, linear constraints on the entries of this matrix coming out of the fact that these operators describe quantum measurements, right? Okay, so since this is this way, and you can always write this matrix, then we can think that the existence of this matrix, gamma 1, is a necessary condition for the probabilities P, alpha, beta here to arise from measurements on a quantum system, right? So the existence of this matrix is just the conditions that must be satisfied in order to claim that these P, alpha, beta are coming from quantum measurements. Now, of course, we can consider higher momenta of this. We can consider a set in which we don't only have the original operators, but we have degree 2 sequences of them, all possible. And with them, we can also construct a matrix gamma 2 here, which will be, of course, bigger. We'll have more entries, but some of these entries will also correspond to this probability, to these probabilities here, alpha, beta. And of course, again, by construction, this matrix must be positive semi-definite, and its entries will be also constrained by the fact that these operators here describe quantum measurements. Now, because the previous set S1 is contained in this set S2, the condition imposed by the existence of this matrix gamma 2 in order to say that the probabilities P, alpha, beta correspond to quantum measurement is stronger than the previous condition corresponding to the previous matrix gamma 1, right? And if you go to from this S2 set to a more general set, Sn, in which you consider in principle all possible sequences of measurement operators of degree at most n, you can again construct a gamma matrix of order n, the entries of which will contain the probabilities P, alpha, beta, and again, these entries will be constrained by the fact that the measurement operators describe quantum measurements, and of course, this matrix has to be positive semi-definite. And the larger the n here you consider in the set, the stronger the condition you are imposing in order to decide if these probabilities P, alpha, beta come out from measuring quantum systems. So at the end of the day, what we have is a sequence or hierarchy of conditions defined by the existence of these gamma n matrices with the strength of the conditions increasing with n. And well, we can use these conditions to compute the upper bounds of the quantum value of a Bell functional in the following way. So again, recall that what we want to solve is this optimization problem here, in which we want to maximize the value of a Bell functional over quantum realizations, right? Now, because these probabilities here, these quantum probabilities here, will appear as elements of the gamma n matrix for a given level n in the hierarchy I just described, then we can write this functional value as the trace here of a given matrix B, which has the same size of gamma n, but some of the entries of B correspond to the value of the functional. And then the trace of this B with the moment matrix gamma at level n in the hierarchy, this will give us the value of the functional, right? So what this means is that we can cast this as an STP, right? In order to compute an upper bound at level n in this hierarchy for the maximal value of the functional. The STP is just this, in which we compute the maximal of this trace I was talking about before, subject to this moment matrix being positive semi-definite, and also with the extra constraints coming out from the fact that we have measurements on quantum systems, right? Now, it can be proved, it is proved in the paper by Navasco, Spironio, Yassin, that this defines a set of upper bounds, a sequence of upper bounds, which I call here beta n, and this sequence converges to the quantum value of the functional, that is the maximal value of the functional over quantum behaviors in the limit when n goes to infinity, right? So the sequence always converges to, at least in finite dimension, to the quantum value, right? So this is a way of deriving a set of upper bounds, a sequence of upper bounds that will eventually converge to the quantum value of the functional. And this is a way in which we can attack the solution of the optimization problem we were talking about. Of course, this is formally the sequence converges when the hierarchy level goes to infinity, but actually there are many cases in which the convergence occurs at a finite level. And the simplest case, again, corresponds to the case of the CHSH functional, in which already the first level in the hierarchy gives the correct quantum value for the functional, right? Is this clear enough? Did I go too fast on this?
I think the overall idea is clear, right? Like you have a way which is coming from up to down somehow, if there is some sort of direction there, to compute the boundaries, no? And this you can do it more or less efficiently with an SDP.
Exactly. That's the whole idea. Okay, we're fine. Okay, so as I said before, for the CHSH case, we have convergence at a pretty finite level. But as before, again, already in the simplest scenario, which is the same of CHSH, I recently have found some results in collaboration with some people in Gdansk, that even in this scenario, you can find Bell functionals, which I describe here with these components here, for which the convergence of this MPA hierarchy occurs at a higher and higher level and possibly infinite. So I'm showing here a little plot. This plot here is, each point in this plot corresponds to the level in the MPA hierarchy in which the numerical upper bound coincides with the actual quantum value of the functional. And as you can see, when alpha and beta go to 0 here in this functional, we have CHSH. And of course, we attain the quantum value at the lowest level, which is 1. But as soon as we start to, let's say, tilt the CHSH functional by adding some contribution of the marginals, we start to see that the required level grows up, and well, it can become possibly infinite as far as we understand. So if you are interested, you can just look at the paper here. But the point here is that even in the simplest scenario, we find weird things as expected at this point. So, okay, what does this all of this have to do with certification? So far, I've just given some ideas on what the boundary of the quantum set may look like. and also I've described a reasonable and pretty common way to attack the determination of the behaviors on this boundary. And now I want to go, as I said before, to the relation between behaviors on the boundary and certification of quantum devices, right? So again, our problem is the one we have here, which is finding the maximal value of a Bell functional over the quantum set. And we can write this expression here in a more compact way here in terms of this W operator, which is called Bell operator associated to the functional, which is basically a linear combination with the functional coefficients of the measurement operators, giving rise to the behaviors. Now, because there is a maximum for a finite maximum for the value that a Bell functional can take over the quantum set, we have that if we compute the difference between this value times identity minus this Bell operator, what we have is a positive operator necessarily, right? Because the quantum set is bounded. Now, because this set is, because this operator here is positive, you can show that it admits a decomposition as a sum of squares, which is what I've written here to the right, where these pi here are polynomials on these operators EAX and EBY, right? So the point is, again, we have the Bell operator, and out of it we can construct a positive operator using the maximal quantum value of the functional. And because this operator is positive, we can decompose it as a sum of squares of polynomials on the measurement operators. Now, if we do this, we know this decomposition exists, but actually finding it is pretty hard, of course. And the point here is that we can again attack numerically the problem of finding this SOS decomposition with an STP relaxation, where what we are relaxing here is the degree of the polynomial. And the point here is that actually the relaxed STP hierarchies we have now on polynomial degree of these SOS decompositions is the dual of the STP associated to the MPI hierarchy that I was discussing before, right? So we have the STP hierarchy for the MPA method that I described before. And now we find that the dual of this is actually a way to decompose this Bell operator in terms of a sum of squares of polynomials on the measurement operators, right? So knowing that these two things are dual of each other, if we know that the MPI hierarchy converges at the finite level, then there is a finite degree polynomial SOS decomposition for the Bell operator, right? And at this point, you may be wondering, why would you do that? I mean, if you can compute upper bounds for the MPA, why would you be interested in finding an SOS decomposition? And the reason is exactly certification. So if let me show you an example. So for the CHS8 functional, the Bell operator looks like this W here, right? Where these X, A, and B, Y can be written like this in terms of the measurement operators, right? Now, you can, I mean, it's not easy to realize this is possible, but it's pretty easy to check that the quantum value 2 square root of 2 times identity minus this Bell operator admits an SOS decomposition. Is decomposition as the sum of 2 squares of polynomials, where these polynomials here are polynomials on the operators ax and by and have this form here. It is pretty simple to check that this is actually true. Now, once we have this, what we can see is that if we construct these polynomials with the operators, measurement operators giving rise to a behavior maximizing the functional, and we act with this operator constructed with the optimal measurement operators on an optimal state, then the result is 0, right? So basically what happens is if we build these polynomials here with the optimal measurements and we act with these polynomials on the optimal state, the result is 0. And what this means is that we have conditions of the form pi acting on psi equal to 0, which are conditions on what the optimal quantum measurements can be, and also what the optimal quantum state can be, right? So not any set of quantum measurements, when replaced in this polynomial, will just kill a state on a given realization. This only happens for the optimal realization. And we have, in this case, two conditions of this form, polynomial acting on optimal state going to 0. And you can check, I mean, I'm not going to do it here, but you can check, and it's not hard to do it, that these conditions, these only two conditions, imply that the only way to attain the value 2 square root of 2 on the CHSH functional is up to local isometries possible. The only way to attain this maximal quantum value is with a state which is a maximal entangled state of 2 qubits, and operators which are in terms of polymatrices given by these expressions here, right? So what I'm saying is you can use the SOS decomposition and the polynomials in the decomposition to show that up to local isometries, there's only one way to attain the maximal value of the CHSH inequality. So if you have, if you're running an experiment and you can prove that you attain the maximal violation in your statistics of the CHSH inequality, then you can assure that what you have in your boxes is a maximally entangled 2-qubit state, and these operators that I've written here in terms of the polymatrices, right? And this is certification of this state and these measurements, or self-test of this state and these measurements. Am I being
just to understand,
here?
Nico?
Yeah.
So for these sets of measurements, the only state that retrieves 0 is the Bell state.
Yeah, actually, this condition here, the polynomial acting on the state going to 0, you can only do it up to local isometries with these measurement operators and with this state, right? And this is, of course, the condition needed in order to attain the maximal value of the CHSH functional. So what I'm saying here again is that there is only one way of attaining the maximal value of the CHSH inequality. So if you're in your laboratory performing measurements and you show me that you have maximally violated CHSH, then I know that you are using some isometry of this maximally entangled 2-qubit state and these measurement operators here on 2 qubits, right? And this is very important for people working, for example, in quantum key distribution and some other quantum communication tasks in which you need to trust or you need to certify that you are using a given set of quantum states and quantum measurements. And there are many DI-QKD protocols that basically rely on maximally violating Bell inequalities in order to certify that the statistics that are being used in the protocol are coming out of these measurements and states. So this is how the idea of non-local correlation, maximally non-local correlations, relates to the notion of certifying quantum states and measurements, right? And of course, this is something I think, yeah, it is here. Actually, this possibility of self-testing or certificating quantum states and measurements is something that you could prove can only occur when you have a behavior that lives on the boundary, actually that behavior that is an extremal point of the set of quantum correlations. So you see, since extremal points always are the ones violating Bell inequalities, you can look for possibilities of certifying local states and states and measurements by looking at maximal violation of Bell inequalities. And in that sense, you can think of looking for certification and certification of states and measurements as some way of studying the boundary of the set of quantum correlations, right? Okay, so bottom line, maximizing the value of Bell functionals over the quantum set, on the one hand, tell us something about how the boundary of the set of quantum correlation looks, but also allow us to find instances in which the statistics of our experiments certificate that we are using a particular state and measurement. Okay, so do we have any question on this before passing to say something about entanglement?
I'm cool. I have a lot of questions, but I took a note. I don't know how the others are. I hope they are still alive.
We can. I don't know how much we've been talking so far.
In principle, we try to restrict the length of the seminar to not more than 1.5 hours, just because we have more activities later. But I mean, it's totally fine if you go on.
Yeah, because I have, well, I mean, the entanglement part is not so long, and I think it's going to be quicker. But if you want, before we go there, we can make a break, or we can just jump to this.
I'd like the others to tell. In the meantime, maybe I have a very general question, which is like from like take home message. When one studies correlations, right? This is some sort of way or path or whatever to understand better which are the limits, no, of quantum mechanics. In this, you know, in our group, like, which is the quantum machine learning group, it's a bit more like from engineering, etc. And the people from our center, you tell like quantum advantage, and then wow, I can do my machine learning algorithms better. And the people care a lot about that. But the bottom line here is like, okay, there are things that with quantum resources you can do differently. I don't know if better is the word, than without them. So my question, maybe if you want to comment a bit, is that maybe correlations are, to my understanding, I don't want to diminish this, but are only one facet, right? Or one phase of a theory. In general, like we also have so when I introduce in the talks or whatever quantum mechanics, I of course I talk about quantum correlations and then entanglement and whatever, but it's not the only thing to study. Is it correct? Like for instance, coherence, or?
Oh yes, yes, yeah. I mean, of course, in the quantum realm, correlations is just a little bit of it. As you know, most of our theories, except for general relativity, everything is quantized, and you have lots of quantum models describing lots of the most various phenomena. And I mean, none of that has to do, at least directly, with correlations. Now, from the point of view of quantum information, I would say that correlations are kind of the thing that actually makes quantum things really, really quantum and separate them from any other possible classical description from nature. And this, of course, includes coherence, because as I'm going to comment now, in order to look for these non-local correlations, you need things that are properly quantum, like coherence between product states and incompatible measurements. So all things that are like properly quantum are needed in order to have these non-local correlations. So I would say, from the point of view of quantum information theory, correlations are kind of the core. Of course, there are many other things, are kind of the core of why you would like to use quantum devices to do things. So yeah.
Thanks for the clarification. I mean, cool. I don't know if others are still alive, but if it's up to me, we can probably go on.
I can't see you, so you tell me.
Cool.
Okay, we follow. So, so far we've been talking about non-local correlations and well, how to spot them and how to use them to do things like, for example, certification. Now, something I didn't say is what is needed in order to have non-local quantum correlations, because since this inclusion here holds in the general case, then we can have many quantum behaviors that are actually local, in the sense that they admit some description in terms of local correlations, right? So if this is true, then okay, we are interested in knowing what makes some quantum behaviors to be non-local, because this is what we are interested in at the end of the day, right? And something that you can prove is not that hard is that in order to have non-local correlations, you need two things. One of them is entangled states, and the other is incompatible measurements, right? Incompatible local measurements. So this means that entanglement is a prerequisite in order to observe non-local correlations, and this is why we are interested in studying it. So in order to define entanglement, it is better to define separability, which is kind of the contrary of entanglement. So as I showed before, the condition for a set of probabilities to satisfy the locality condition is this equation here, right? Now, we know that if we are using quantum devices, then the probabilities are computed via Born rule. And it's not hard to see that in order to have factorizing probabilities, like inside the integral here, we need to have states that are either products or some convex combination of product states, right? So in order to have, or in order to characterize the set of quantum states that will give us correlation satisfying the locality constraint, it's not hard to see that the most general form of these states is this one I have in the equation here, and these are called separable states. So if we have a state with this shape here, then there's no way we can have non-local quantum correlation, right? So how we define entanglement? Well, as the opposite of separability, right? So an entangled state is a state that is not separable, a state that in the general case cannot be written as some convex combination of product states on the two sides. And of course, this generalizes to more sides, but we will just remain in the bipartite setting. Okay, so the set of separable states contains all the density matrix that can be prepared by means of some local operations in classical communication protocol, right? Something like local preparations using shared randomness, for example, or any protocol, preparation protocol with that shape will give us a separable entanglement. So this means that we can think of entanglement, and this is how people in quantum information theory thinks of entanglement, as a form of correlation that cannot be generated via any possible protocol involving only local operations and classical communication, right? Now, this is a very useful way to think about entanglement, because this means that this is the correct context in which entanglement is a resource, in the sense that we can use it to do things. So the point here is, or the bottom line here is that if we cannot generate entanglement via LOCC operations, then it becomes a resource when our allowed dynamics are restricted to operations in the LOCC set, right? And the simplest example of this is the teleportation protocol, which I think you all know, right? So in this case, what we are using is the entanglement in between Alice and Bob qubits A and B to perform a non-local operation, but in the context of dynamics restricted to local operations in classical communication, which is exactly what this protocol does. So in a general frame, we could think of entanglement as that allows us to implement some non-local operations, even when our dynamics, for whatever reason, are restricted to local operations in classical communication, right? Okay, so in that sense, we can think of entanglement as a resource, and we can build a resource theory for entanglement, right? And in that sense, we can think of separable states as a state having no resource, which are free, and on the contrary, entangled states as states having some resource that we will call static resources. In the same way, we can think of operations in the local operations in classical communication set as operations that are free in the sense that they cannot generate any resource, whereas entangling operations are considered dynamic resources, because this is something that can increase the amount of resources that we have, right? So this is the way in which most of people in quantum information community thinks about entanglement. It is a resource that you can use to do things, and it is useful to think about it in terms of a resource theory. So because this is a resource, once we understand what is the context in which it is a resource, the next thing we want to do is to quantify it. So the point is, well, how do we quantify this resource? And I mean, there are lots of measurements because of measures of entanglement, because the literature on the topic is literally endless. But there's one key observation that I think is like the one important and the one that will help you to understand what entanglement actually is and how to quantify it. And is that when we measure a quantum system, we acquire information about the system. Sorry, about the state of the system. Now, this in terms of words can be vague, but there's a formal way to express this condition. So suppose we have some state rho, and on this state we perform a measurement which is described by some measurement operators here, mk. Now, if we do this, then when we obtain outcome k for the measurement, then we have that our state is updated in this way, right? And the probability is given by this expression here, because it is again the Born rule. Well, we can prove, it's not hard to prove actually, that the ordered descendant order vector of eigenvalues of the original state is majorized by, well, in average, majorized by the set of eigenvectors, ordered eigenvectors of the conditional states rho k, right? So this relation here is majorization. I think you all know it, but just in case, this means that the guy on the left is majorized by the guy on the right. And in order to decide this, we basically order the vectors and take partial sums. And for all partial sums, we have this inequality here holding, right? Now, on a more intuitive way, what majorization means is that the vector on the left is more disordered than the vector on the right, right? The distribution is nearer to the uniform distribution on the right than on the left, right? So this is a way of thinking about order, and this is somehow related to the notion of order related to entropy on statistical mechanics. But again,
Nico,
this is
sorry,
yeah.
just to be super short. The more the order is, how do you say, the most disordered, the more like the mixed state majorizes everything, right?
Yeah, it's majorized by everyone. So the more ordered guy majorizes the more disordered guy. Okay.
The more ordered guy, for instance, okay, because I have one.
Exactly.
If you want, so you have only one, and then the partial sum is always bigger. Okay.
Yeah, exactly. So the guy that has one and all zeros, that's the most ordered distribution possible, and the most disordered distribution possible is uniform. And then, well, you have everything in the middle, and more order means you're majorizing the more disordered thing. Now, the thing of this is that this is a kind of formal way of expressing this idea of that of acquiring information about the state of our system out of performing a measurement. If we perform a measurement and in average these eigenvectors get more order, that means that the entropy in average is decreasing, and that means that we are nearer and nearer from a pure state. And once we have a pure state, we have all the knowledge that we can have about the quantum state, right? So this is more or less the intuition behind majorization as a way to express how we acquire information. Now the thing is, this relation here holds every time we want to perform a measurement. So if we have now a bipartite state, and on this bipartite state we want to perform local measurements that will be in general described by Krauss operators like this tensor product here, then a similar relation holds for local states, right? The marginal states of rho A, B would be called rho A or rho B. And again, since the measurements here are local, the evolution of the marginal density matrices will be the same as before. And for both marginal states, we will have that the majorization relation is satisfied. So this means that when we perform local measurements on a bipartite state, what we are doing is learning about local states. We are ordering the eigenvalues of the local states. So if this is true, then if this is true, then what we can think of is that, well, whenever we have a function that preserves this majorization order, this function will have a monotonic behavior under local operations in classical communication, right? So for example, if we have this pure state here, right? We can, with these Schmidt coefficients here, square root of psi, then you can check, because it's just a direct computation, that the eigenvalues of both reduced density matrices or marginal density matrices have the same eigenvalues, right? These two guys have the same eigenvalues. And now we know, because we just saw it, that if we perform local operations on this state, then what will happen is that the eigenvalues of both marginal density matrices will be more order in average. So this means that if there is a way to transform this state psi on this state phi via LOCC operation, these are two pure states, then it must be true that the Schmidt coefficients of the original state are more disordered than the Schmidt coefficients of the target state, right? And this is a theorem. This was proved by Nielsen around, I don't know, like the 2000s more or less. But this more or less encodes all that you need to know about bipartite entanglement. When you perform local operations on a bipartite pure state, what happens is that you get a set of more ordered Schmidt coefficients in the Schmidt decomposition here, right? Okay, so this pure state conversion via LOCC operations is possible only if this majorization relation holds. Now, it follows, as I said before, it follows from this theorem that if we have a function that preserves the majorization order, then this function will behave monotonically in their LOCC operations. And then this means that we can use it to quantify entanglement, because a measure of entanglement should be such that it has a monotonic behavior under LOCC operations, so that we can see that performing free operations on a resource theory, which are LOCC, does not increase the resource, which is entanglement. Now, the set of functions preserving majorization relation is very well known. These are known as shared concave function, and the most important member of this class of concave functions, is the von Neumann entropy, which is given here. So you could think that we can just quantify entanglement in a pure state just by computing the von Neumann entropy of the marginal states, right? So in a bipartite state, in a bipartite pure state, the two marginal states are the same. So you can compute von Neumann entropy of either one, right? And this quantity here is called entanglement entropy. Now, so far so good, but there's a difficulty here, which is that majorization is a partial order. It's not a total order relation. What this means is that some states, some pure states, will not be comparable, right? So we will not be able to decide just based on majorization if two given states are more entangled, if one state is more entangled than the other. This will not always happen. So, but we can solve this problem, or we can attack this problem, by considering a more relaxed set of operations or transformation protocols, which is asymptotic transformations. So far, what we have been thinking of is to just how to transform one copy of a state into one copy of another state via LOCC. Now we can relax this and think of transforming a bunch of copies of the original state into some other bunch of copies of the target state, right? So the number of copies in the original state is n, and the number of copies on the target state is m. Now, if we are able to do this for some values of n and m, in the limit of large values of n and m, the ratio between n and m, the ratio between original states and converted states, will indicate us the relative entanglement between these states, right? In the same way as before, because what we are doing is converting one state into the other by LOCC transformations. Now, if we think of this in these asymptotic transformations and in the limit of many, many copies, there are many measures of entanglement that we can come up with that will depend on, well, the particular task we are carrying and the particular LOCC protocol we are implementing. Now, out of this, there are two. There are the most relevant. The first one is entanglement cost, and This is given by an equation and optimization problem, which I will not dive into, but in terms of words, entanglement cost is a measure of, for a given state rho, is a measure of the rate at which you can transform Bell states, blocks of Bell states, into some copies of this state rho, right? So it's like the amount of maximal resource states that I need in order to create copies of my state rho. And this is entanglement cost, right? Because this is a way of saying how much it costs to create copies of my target state rho. The other measure is entanglement distillation, and this is kind of the reverse of the other one, because here we are asking for a given state rho, the rate at which this many copies of this state rho can be converted into maximally entangled state of two qubits, right? So we're kind of distilling how many Bell pairs we can get out of copies of this state rho, right? Now, these two things are in general different because they are defined different, but it turns out that in the case of pure states, these two quantities have the same value and they actually coincide with the entanglement entropy that we have defined before. So what this means is that if we relax our protocols from one copy transformation to asymptotic transformations, then we can impose a total order in the set of quantum bipartite pure states that turns out that takes entanglement entropy as the only measurement of entanglement that can decide whether one entangled state is more entangled than the other, right? So this is a way to bypass the problem of majorization being a partial order relation and having a reasonable measure of quantum entanglement in bipartite pure states. Now, once we leave the set of bipartite pure states, everything gets like very, very crazy, and I won't go there because we don't have forever here. But I just can say the following. The main problem when going to from bipartite pure states to multipartite pure states is that we lose the possibility of defining a total order in the set of quantum states in terms of entanglement. So it is still true that when you perform local measurements, the local states get majorized by the conditional states in average. So this is still true, and you can still use this to define entanglement monotones. But it is not possible to define a total order relation that will tell us in an easy way whether one state is more entangled than the other. This means that we have to kind of relax not only the kind of protocols that we implement in order to decide how to convert the states, but also we have to relax even the set of free operations in a resource theory and start considering instead of one-shot transformations, just probabilistic transformations, and this gives rise to another much larger set of free states, of free operations, which is the set of stochastic local operations and classical communication, which is very, very hard to understand, and maybe we can talk about it on another time. So far, this is, I think, this is the most important thing to kind of know and discuss on non-locality and entanglement, how these two things are related, how this is related with certification and reconstruction program for quantum theory, and so on and so forth. So this is it. And if you have questions, we can just discuss now. If any of you is still alive.
I hope people are, yes, Fernando is alive. Thank you very much, Nico. I think it's a super big effort to speak about so many things that maybe for one coming a bit from the background of quantum info is kind of the daily life, no? But to condensate this in a talk is not a trivial task. So really, thank you a lot. I have a lot of questions, but I would like if more people want to speak, like the floor is super open.
I don't have any specific questions because I still have to digest all this, but thank you very much for the talk. It was really interesting.
Yeah, there are many things that I couldn't include that for sure you will be interested in because, well, I mean, as I said, this is too long and we don't have all day here. But in terms of deciding whether some behaviors are quantum or not, this is something I've talked about with Matti. Of course, you have all these STPs and outer approximation to the set of quantum correlations and everything. But one thing you can do, and I tried to do, not with very much success, but I tried anyways, is to recast this as a classification problem and try to train a neural network to kind of see if I can, out of the training of this, have some approximation to the boundary of this set. And in the simplest scenario, it kind of works, but I'm not sure it's an efficient way of attacking the problem anyways. So, I mean, if you are interested in this, I can just give you the reference.
Sure,
Absolutely.
100%.
I'm super interested in that. And so please let us do it in some way next.
No, I can look for it and pass it on the chat.
Absolutely, yeah. One of the things that we also were, first of all, thank you very much for the masterclass. Really amazing effort and for the synthesis, and hardcore for us that even some of us, we studied physics like in the Paleolithic, going on for recent days for the rest of our career. It's quite motivating. One of the questions that I was mentioning that we have discussed also within the group, in which we have computer scientists and also physicists and mathematicians, is kind of an entry point of how to what extent this entanglement can be approached in the initial steps, right? In order to get into the quantum machine learning, for instance, right? And my question is more in the case of to what extent it is too much. For instance, we have had internal discussions in which eventually we could identify different the superposition of different models, or these models could be entangled, as a matter of fact, which are not exactly something related to physics, no, but more in a more, let's say, philosophical way, no. This for computer science is very important because in some way provides with an entry point to what is the benefit that I can get, right? If I include the concept of entanglement of quantum correlation into my line of thought. And internally, this is one of the most difficult aspects to tackle, also with the students. I don't know if you have thought about any pedagogical way in order to, and you did an excellent work, to provide a solid mathematical background in order to do that, right? But now I'm thinking about more something more in the intuitions or the benefits for computability.
Yeah, I mean, I would say intuitively, this thing that I outlined is, I mean, at least to me, the simplest way to understand these things, which is from an operational point of view, right? So it's like you have some experiment, you measure things, you have some measurement statistics, and you want to understand what happens with these joint probabilities when you have quantum systems. And the simplest way to look at it is from the negative way. It's like, okay, in many instances, you will have correlations that, even if they come from quantum systems, they can be simulated with classical systems. And these are all that comes from separability, right? So this is not interesting in terms of correlation, because this is something we can do without quantum systems. What we can do with quantum systems that is interesting is all of this that cannot be done with separable states and also compatible measurements. So I would say that the core or the actual research is on one hand having non-separability and having non-compatible measurements. So on the side of non-compatible measurements, the fact that you have measurements that in your theory you need to describe, because there's no other way that we know, as non-commuting operators on a Hilbert space. This is one of the things that really separates quantum mechanics from classical theories, and is one of the things that you really, really need in order to have non-local correlations. There are the interesting kind of correlations. And on the other hand, the fact that there are non-separable states, what means is that because your joint Hilbert space is actually a vector space, you have the possibility of have coherent superpositions of product states. And this is something that you cannot do with any protocol that involves just only operations on separate laboratories and the amount you want of shared randomness. It's just not going to happen. And this comes from the very mathematical structure of the theory that allows you to describe states in terms of vectors in a vector space, and allows you to find solutions of your equations of motion, which are linear, as coherent superpositions of solutions. So I would say these are the two things that actually make it all in terms of what really is quantum. One is coherence between product states, and this is basically entanglement, and the other is the possibility of measuring things that do not commute, in the sense that it's not the same to measure in one order or the other. And all stems out of this.
There are infinite things to talk about this. With Fernando, when we started the group, and I guess until now, and for the next 3 centuries from here on, I believe there is an open question, in which maybe now you have all these, apologize for the word, but all these bullshit NISC things. But
I
think it is a genuine question, and I consider it is like our research question with Fernando, which is how can you identify the boundary between to make this balance of the trade-off, no, of which things one community needs to be instructed which is like how do you speak with computer scientists that maybe did not pay enough attention because they never needed to linear algebra and multiply matrices. Even I'm not saying about the CVC, but other people here in La Plata, they speak openly that they don't know how to multiply matrices, but they are working on quantum software. And which are then the question is like, okay, how, if there is any sort of overlap between things these two communities do well, no? And if that overlap can be named quantum machine learning or quantum computing or whatever, then which is the stuff that one needs to explain from one community to the other. And this
Well,
is bidirectional, no?
You just have destroyed the only bridge I thought we had, which was linear algebra. Because I think that's the only bridge that we actually have, and we have to use it. Because at the end of the day, everything is linear algebra. And in finite dimensional systems, that's all we need. And actually, only matrix algebra is all we need. So, I mean, because of course, I'm a physicist, and of course, for me, the state of a quantum system is a vector on a Hilbert space, and is as abstract as you want. But as I said to my students the other day, in principle, if you know how to multiply matrices, and you know about some linear transformations in between real spaces, that's what you need. You don't need to talk about Hilbert spaces and some other more sophisticated stuff, because if you're working on finite dimensional quantum systems, all you need to do is to find the right matrix and just do the multiplications you need to do, and that's it. So I would say, I mean, I think it's just wrong that people working on quantum software doesn't know how to multiply matrices. That shouldn't be. But if we take that aside and we assume everyone knows how to multiply matrices, I would say this is how we should communicate. And people from physics should start or should stop talking about fancy things like Hilbert spaces and just start talking more about how to multiply matrices. And people from computer science should be like more comprehensive with people coming from physics, because we don't think in the same way, and and you can tell that's true. But yeah, okay. I mean, I would say linear algebra is all we have for now, because I mean, I don't expect someone coming from computer science to actually take like 2, 3, or 4 courses on quantum mechanics or quantum field theory or whatever. It's just not going to happen. It's not realistic.
No,
but
also
we do have linear algebra.
Again, just to try to sum up, because we can really be speaking for years about this. You mentioned that you were applying like a PCA or support vector machines or something like this for this classifying detector of the boundaries, etc. So to put this into more general perspective, no, which tools do you, or which tools, ideas, or whatever do you think are relevant for people having this expertise, no, to apply in, no, which kind of problems beyond this problem that you have tackled, no? Because if maybe applied computer scientists, which are not which do not represent the whole set of computer scientists, maybe are not that good multiplying matrices, but are extremely good at training support vector machines, way better than us physicists. So the question, I think, is really there, no? How can we have a proactive, no?
Well, you're right in something. Linear algebra is not the only bridge we have. The other one is convex optimization. People from computer science knows lots of convex optimization that I don't, and we have a tendency to define many things as the solution of some convex optimization, expecting someone else to solve it. So I would say that's another bridge there. And of course, I mean, the tools from machine learning and neural networks and all of that are very nice and very welcome to solve convex optimization problems. And well, this is something we should talk about. This is, I mean, these tools I just know only on the surface. And I mean, if we can collaborate, like in combining your expertise on machine learning and everything, and my expertise on defining problems to be solved by someone else, well, maybe we have some.
So there is this niche that we always try to. I mean, if a whole community is working on something, then this is a clear sign of like a dictatorship, no? Like, and if you ask in an audience in a conference in, I don't know, quantum machine learning or quantum info or applied quantum information or whatever, what are them asking and who, what are they working on? And if who is working on variational algorithms, maybe 80% will raise their hands. No, this is worrisome because not just because we have close friends that demonstrate that this is useless, but also because it's very unified, no, and very centralized. And this is not good for science. So one of the moves that we want to do with Fernando is finding meaningful research directions that go beyond the variational algorithms, no? And the main outcome of your talk that I get in this line is that there are research directions that we could take. For instance, applying the techniques that we know how to handle with machine learning and whatever, for example, in complex optimization.
Yeah, sure. And I mean, again, I know almost nothing about how to combine machine learning with quantum computing or quantum systems in general. But I think that maybe in trying to use classical machine learning tools to solve quantum problems, we may find some problems which may actually require quantum hardware combined with machine learning in order to have efficient solutions. So, I mean, I'm more of the direction of let's try to exhaust our classical things to solve quantum problems. And once there's nothing else to be done, well, let's think about how to use quantum to solve what can't be solved classically.
Cool. Well, Nico, thanks a lot. I think it's been already 2 hours. And personally,
that's a lot.
I'm super good if I take a break. But I don't know, Fernando, Oriol, there's Some, and Sherai. From my side, really thanks a lot for your effort and joining us today. Super cool. I personally learned a lot, actually.
Yes, thank you, Nico, for the generosity. I think for having synthesized this intense hour and or two.
Yeah, it was. I'm aware it was too much. Actually, it was longer. I should.
No. Thank you very much for the generosity.
But
time.
Yeah, but I mean, if there is something on the many things I kind of pinpointed that you would like to go deeper, and for sure we can arrange something and be more.
I think that we will definitely do. We are now digesting a number of actual, let's say, mini toy problems that help us to converge. And definitely, I think that we will come across. But this, let's say, approach that the breaching through linear algebra and complex optimization that you clearly highlighted and identified, it's also, which sounds like trivial, but it is not in the as a programmatic effort, which is what together with Matthias and Paula and Oriol we are doing here. I think it's very, very constructive, and your talk has in some way provided us a horizon. I see that as a horizon that in some way make us think about which is worthy, right? To invest time on in terms of the tools and in terms of the formalism. So thank you for that. It helped a lot to me also.
Oh, I'm glad.
Okay. Catch you super soon, and have a super nice day. I need to go, but